Good day, everyone, and welcome to lecture 10 in ordinary differential equations. So in this week, we're going to learn how to solve linear systems in case when the matrix has complex eigenvalues, and we are also going to touch a little bit about nonlinear systems of differential equations. So here is the list of things that you need to have known before you do this lecture, with one little exception. That this is not really required. It may be the simplest thing out of this, but it kind of has been here since last year, so I forgot to remove it. So power series you don't need, but eigenvalues, eigenvectors, that kind of stuff from linear algebra 2 is going to be very important to understand this lecture. So recall that the last week we learned how to solve linear homogeneous systems with constant coefficients, right? So such system is just the right-hand side of such system is just some constant matrix times the unknown vector, right? And to solve it, we need eigenvalues and eigenvectors, right? So here is the general formula, right? So we have this eigen. So yeah, let me maybe remind you. So what this is. The fact that xi1 is an eigenvector means that A times xi1, it's a vector, is R1 xi1, and so on. Yeah, but of course, strictly speaking, it works with for complex eigenvalues, but for complex eigenvalues, it is going to produce complex answers. So another problem with this formula is that it requires n linearly independent eigenvectors. So which means that in order for this formula to work, the matrix A has to be diagonalizable. So in today's lecture, we're going to cover the case of complex eigenvectors, but we're not going to cover the case of non-diagonalizable matrices. So for systems of two equations, it's easy to sketch phase portraits. Basically, there are 3 different types. And if you don't need to sketch or plot, if you just want to distinguish between these 3 types, then you don't even have to calculate the eigenvalues. You can extract this information from just them being positive or negative. All right, so that's all we